Okay, so today we're going to talk about the BFS, breadth first search. And if you know already, maybe take this chance as a reviewing. So let's warm up our brain. Problem day. So present the correct and efficient algorithm to convert between the following graph data structure for undirected graph G with the n vertices and m edges. You must give a complexity of each algorithm. Number one, convert from adjacent matrix to adjacent list. What's the efficient way to do this? Okay, let's think about 4 or 5 minutes. Then we're gonna discuss what does. Then I'm gonna ask, what's 1.5? I'm gonna ask Ulbek and Yuha and Suin, and if possible, and Tejun. Okay, so let's solve this. So you understand that, right? So we have a graph structure. One is structured in adjacent matrix, and I want to convert it to adjacent list. What's the fast and efficient way to convert it from adjacent matrix to adjacent list? So adjacent matrix, something look like, oh, this is 1, 1, 1, and 1, something like this, right? Everything else is both 0, and I want to convert it to the list. Okay. So what's the best way to do this? Let's think about 4 or 5 minutes, and we're going to discuss about it. Okay, ready? Pull back.
Here, I'm not sure how to do it exactly, but
Don't worry.
maybe I'm not sure how to do it. How to convert it.
Okay, so Yuha?
Yes.
Hmm.
I think I'm gonna make an array of lists.
Array of list. So your
Yes.
job is converting matrix to adjacent list.
Yeah,
You
so like the adjacent list would be like, they would kind of be like an array of lists. So every row, every index would be like a list. And then I'm gonna traverse through the matrix every row. And then if they are like connected, then it's a 1. So for every 1, I think I'm just gonna add the corresponding like the x, I think, like to the index I of the list, I think. Just append it.
matrix. So I comma j is 1. So you're gonna make a 2 loop. J
Yes.
is 1 to n. Then if n, then add 2.
Index I of the list. Add j, yeah.
List on I to add 2 list i's as a j. Something like this. Okay, what's the complexity?
O n square, I think.
Yes, good. Okay. There's someone, can you bit this? Is there someone who can bit this? Okay, how about, thank you, Yuha. And Swin?
I have the same idea with Yuha's algorithm.
Okay.
Yeah.
Okay. I think I can make faster. And Taejun?
I don't think mine is better than that, so I was still working on it actually.
Okay. Anyone else? Nobody? Okay, look at the character of the matrix. Matrix is, if this is 1, then this 1 appear. If this is 1, then this 1 appear. They are symmetric, right? Because if 7 to 3 is connected, then 3 to 7 is also connected. 1 to 7 and 7 to 1, something like this. They're all connected. Then how can I make better than this? For I to n, I to 0 to n. For j is I to n. Why is this possible? Because I don't need to be here. I only need to from here. Right? Then from I only can scan those, which reduces half of the computation. Then do the same thing. If matrix of I, j is a value, then add to list. Yeah, subject list. Okay. Do you see how I've done? So matrix has character. I don't need to fully scan through. Then I can make this, which computation is Like zeta of n squared. But the computation wise is almost half. Right? Does anyone has better idea? No? Everybody following what I'm doing? Maybe too quiet. Okay. So let's go back to the slide. Now I can do it in zeta of n squared, which is actually half of the n squared, right? Then let's do the second problem. Second problem is now from adjacent list to the matrix. How can you do this? How can you do this in a faster way? Okay, let's think about for 5 minutes. Then let's talk about this in 5 minutes. Okay. All right. So in 5 minutes, I'm gonna ask. PK and Hasong and Seung-jae Kang and Kwang-min. PK?
Well, I'm not sure the answer,
Don't worry.
but like for the matrix, like if you can imagine that like can be the matrix will be like I don't know. I really don't know how to answer this.
Okay. Okay. 하성? 전하성?
Yep.
Yep.
So I think like for 0 to n, if we revisit for the base case, if we revisit all the nodes, we simply return. Otherwise, if there's a vertex remaining on the linked list, we put the maybe matrix ij equal to 1. We declare a matrix I comma j equal to 1 and do the same thing recursively over and over.
So you're gonna do init matrix and count list. Which what starting. This will figure out number of vertices. Then for I to less than 2, 1, 2, n, and list I point next. So it should be while. So J. So J is 1 while list I dot next is available, then J is plus plus, then fill matrix, the visit of I and J. Is it what you're gonna do? Basically it is, right?
Yeah.
Okay.
And I think the complexity is O and M.
O and M, how come?
Yeah, because we
How?
visit the all vertices and we visit the only edges.
Okay, good job. You are Hasong, right?
Yeah.
Hasong. Okay, thank you. Kwangmin, do you have different idea? Kwangmin? No? No respond? Is it not here? KM. Maybe he's not in here. PK. That's Kwangmin. Oh, I catch you. You are not here. I thought I saw his name. Okay. Anyway, he's not here. Seungjae?
Professor.
Yeah.
I'm not pretty sure about it.
Okay, anyone else? Okay, I think Hasong did a great job. Right. So complexity is M by M. Why? So I visit all my vertices and I keep going to the next. Also, if it is more efficient, I can fill in matrix IJ, and so inside of this function, if IJ, then I'm able to fill in JI too. Because the addition list, if it is 1, it should be 1 too, right? So this is a simple job to do, and if it is if there's next and next, then can I reduce it? Because there is a duplicate, right? Is there any mechanism to reduce the duplicate? So there is a duplicate, right? Because 1 to 4 is 1 to 4, 5, and 6. Then if this means 6 has 1, and 4 has 1, and 5 has 1. How can I eliminate? How can I reduce this? Do you see what I do? So like we did in the, like we did in here. Can I reduce this? Because it is duplicate. How can I reduce this? Can we?
I think we cannot do that.
We cannot?
Yeah.
Okay.
Because there's some self-pointing edges.
Self-pointing addresses. Okay.
Yeah, so you need to traverse all the vertices. Yeah.
Okay, anyone else? Seungjun, thank you. Anyone else? No? Okay, so briefly, it is not possible because if we do this, I want to do that. So 1 to 4, oh, 4 to 1. Then I go to that 4 to 1. This complexity is more complex. This process more complex. And I have to do stop here, go to there, and stop here and go to there. What is this? This is basically DFS. Dig in here. From here, this guy, I want to discover that. And dig in there, the DFS. That's more complex than doing this. But rather than I'm just scan it through, which is the big O n by m. I don't need to care about all big O n by 2 by m because I have duplicate. If I am more efficient, maybe I can do m by n. But this 2 to 1 is illegal and more complex because I have to do DFS, dig into the more. Okay. All right. So go back to the slide. Okay, we solved it. So today we're going to talk about the graph and the BFS. So one of the most fundamental graph problem is how to traverse the edges and vertex in the graph. How to do? Well, we have many mechanisms. We can do DFS or BFS. We can do more complex thing. Okay. So for the 373, so we're going to do DFS, BFS. Then we're going to talk about the backtracking. So for the efficiency, we must make sure we visit each edge at most twice. Why is it at most twice? Why not 3 times? Why not 1 time? Okay, we're going to talk about it. So for the correctness, we must do the traverse the systematic way. Then we don't miss anything. We have to do correct answer, the core of the algorithm. And since a maze, you know what the maze is, right? That's from here, all the walls. Oh, wrong, then come back. Wrong, come back. Oh, correct. There's something like this, or maze. So maze is just graph. Such an algorithm must be powerful enough to enable us to get out of the arbitrary maze. Okay. So marking vertex. Marking vertex is critical. We have 3 mechanisms: unvisited, discovered, and processed. Initially, it is all undiscovered. Then if I visit them, just it is discovered. Then if I process everything, meaning I calculate all its adjacent, then it is processed. Okay. The key idea is that we must mark each vertex when we first visit it, then keep track of what have not yet completely explored. What is the difference between visiting and completely explore? Visiting means, oh, I can see you are there. Then it's completely explore means I know who you connected to. So your adjacent list are all discovered. Okay, you're explored. Oh, I know you are there. Oh, I can just notice you, meaning I just visit you. Okay, discovered. I just discover you. I just processed you. Undiscovered. Oh, it is unknown yet. Okay. So to-do list. So to-do list is maintaining what to do in the visiting process. So to completely explore the vertex, we look at each edge going out of it, meaning we have the steps. Undiscovered to the discovered to the processed. Okay, so regardless of what order we fetch the next vertex to explore, each edge is considered exactly twice. Why? So BFS, I got them here. If I starting from here, this guy and this guy, then this guy do it, this guy and this guy. If you look at the sequence, I just discovered this. Discover, 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 discover. Oh, explored, 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 explored. I just visit twice. Visit twice as visited, explore. Okay, completely explored. So open it. Oh, I'm to do. To do, go to there. Okay, if I draw again, say I have very simple graph. From here, oh, I just discovered, oh, you know what? I have adjacent list. Okay, I open it. Oh, adjacent list, adjacent list. And this guy, adjacent list, adjacent. You know what? I have nothing to do. I have nobody except you. Then I am processed. oh, I have no one else except you, processed, then from here sequentially, processed and processed. Okay, to-do list. I visited twice, visited and processed. Okay. And correctness of the graph traversed. So each edge and vertex in a connected component is eventually visited. So unless it is not connected, if it is connected, it will be eventually discovered and visited. So suppose not, there exists a vertex which is unvisited, whose neighbor was visited. So neighbor is eventually explored, so it would visit it in the end. So let's talk about the BFS. So Bayesian operation is most common graph algorithm is completely and systematically traverse the graph. And we want to visit every vertex and every edge exactly once in some well-defined order. So order in sequence, we call the BFS or DFS. BFS is appropriate if we are interested in shortest path on an unweighted graph. So we will kind of talk about it. And this is data structure of the BFS. We use a Boolean array to maintain our knowledge about each vertex in the graph. The vertex is discovered for the first time we visited. Then vertex is considered processed after we have traversed all outgoing edges from it. Okay. Then once the vertex is discovered, it is placed on FIFO queue, then to-do list. Then all this vertex to the closest root are expanded first. From expanded, then from there discovered. From here, visited, explored. Okay, sequentially. So initialized BFS is everything as a false, and parent is a root. And BFS example, let's do this. From 1, I go to 2, 5, and 6. From 2, go to 3, 5, go to 4, 6. Oh, I have nothing to do. Then from 3, oh, no, I don't need to do this. Then completed, 4 completed, 5 completed, 2 completed, 1 completed. Okay, back to here. 1, 2, 5, and 6. From 2, 3, and 5. 5, I don't need to do that because it is already discovered. It is on my list. Then 5 goes 4, and 6 has nothing to do. Okay, I'm processed. Then 3 and 4. Then 3 is about to discover that guy, but it is not necessary because it is on my to-do list. Okay, so I'm finished. 4 is finished, 5 is finished, 2 is finished, 1 is finished. Okay, sequentially. Okay, exploring traverse. So we can easily customize what the traverse does it to make one official visit to each edge and each vertex. By setting a function to do is vertex and edge, and we print each vertex and then edge exactly once. So finding path, the shortest path kind of thing. The parent array sets within the BFS are very useful for finding interesting path through a graph. Okay, the vertex which discovered vertex I is defined as parent. My parent. So what is good thing to do parent? Meaning, hey, I want to go from one place to the other. Then your cities are represented as the vertexes, and this road is edges. Okay. Hey, with the many way, there is not just one way, because I'm in the road configuration. If I reach there, your destination, then how can I find the solution, the best one? So by doing a BFS, less one. Let's say I want to go from Songdo to Seoul. So outgoing Songdo, let's say I have 3 bridges. I can take this bridge, and this bridge. Then I can go to the multiple different cities. From there, how can I get to Seoul? This one. There will be multiple choices. It doesn't need to be 2. It could be multiple choices. Then there's all diverses. Then you reach the Seoul. Whatever it comes first, then I can take this one by reversing back. How can I reversing back? Because I have a parent. My parent is my parent, my parent. So less hops giving me less complex. Then there is more and more and more. There will be soul, 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 and soul. So what is the best way to do? So if I'm considering all the weight is summed it up in the view of the time, in the view of the ton, in the view of the cost on the toll gate, then I can consider, okay, this one is the best if you consider the less turn. This one is the best if you consider inexpensive. This toll is the best if you only consider distance. Okay, something like this. Then BFS is common mechanism, common solution for the shortest path, because we can roll it back, then we can find the best solution, best path to there. Okay, so shortest path and BFS. In BFS, vertices are discovered in order of the increasing distance from the root. Okay, we just observed it, increasing. Okay, the unique tree path from the root to any node uses the smallest number of edges. It could be multiple for the destination based on the configuration. And equivalent, so possible any root to X path to the possible. Okay, what does this talk about? So this means say I reach here, because I have the concept of parent, then I can roll back, then I can find the source to destination more efficiently. Okay, so smallest number of edges possible, any root to X path described. Smallest number of edges, smallest hop, smallest hop, smallest hop. If you consider that distance is the matter, then you can change the edge in different configuration. Then you can find the shortest path from A to B. Okay, that is the configuration in the BFS. If you use a DFS, it will be a completely different story. Okay, so the shortest path, the BFS is common solution. Okay, recursion and path finding. So we can reconstruct this path by following the chain of ancestors from X to root. This is the key, X to root. Note that we have to work backward. Why? We cannot find the path from the root to X since the node does not follow direction of parent pointer. Parent has the child has many options, many candidates, but the child to parent only one. And parent is one, parent one. There's much faster. Okay, so instead we must find the path from X to root. That is right approaches. So the recursion and path finding. So when we do this, so from there is many candidate, then I found that by the BFS, I found the solution. Then from there, roll back to there. How can you do? Because I only have one parent. I only have one parent. Parent may have multiple children, but children only has a single parent. Okay, so this is how you do the BFS. Okay. All right. Okay, let's pause in here.